This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. In today's topics, we'll see physical significance of divergence. Actually, so basically, what is divergence? So here then we'll see in detail what is the divergence of velocity and how do we relate the divergence with respect to any fluid element or a control volume which is moving with respect to space. Right? So before knowing this divergence, so let's see some vector entity and what is divergence we'll see. Just we'll recall that. Right? So basically we see the gradient operator. So this gradient operator del is called dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. Fine. So we have this. So basically this is our gradient operator. Fine. So next velocity. So let's say this is velocity u bar. So which is u of I cap plus v of j cap plus w of k cap. So we have this equation. So now basically when we do the dot product of these two vectors, which is del bar plus u bar, so which is equal to dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. Dot product of next u of I cap plus p of j cap plus w of k cap. Fine. So finally, so when we do the dot product, what happens? Dou by dou x of u plus, so when we do this one, what happens? So we have I dot I. We have vector entity we are seeing. So I cap dot I cap plus dou by dou y of v j cap dot j cap plus dou by dou z of w k cap dot k cap. Okay, so we have this. So in a vector entity, when you do dot product I dot I, we take it as 1. Fine. J dot j, we'll take it as 1. K dot k, we'll take it as 1. Okay, that's why we'll take this as 1. Therefore, the resulting equation, so the resulting equation del dot u bar, so which is equal to, so dou by dou x of u plus dou by dou y of v plus dou by dou z of w. So this is our resulting equation. Fine. So here what is happening actually? So even though this is our resulting equation, so this divergence, so del dot u is equal to, so here we will take this one as 0 actually. So the meaning of divergence of velocity is like, so here del dot p bar, here we will take it as 0. Okay, or this is for the Laplace equation. So this del dot dv actually is called the divergence. Fine. So this is what divergence of velocity. So anything, let's say you take del dot of any vector you take. Okay. So let us take the force vector gradient. So the divergence of force we'll say. So here basically f bar will be of f of x I cap plus f of y j cap plus f of z k cap. Okay, so this is what you have actually. So f bar is nothing but f of x I cap, f of y j cap plus f of z k cap. Fine. So here what is happening? So when we do the divergence, so the vector entity vanishes and you have the derivative of the entity. So the derivative of the entity will be will become the change in the direction, or let's say the change in that particular variable with respect to independent variable x, independent variable y, independent variable z. Okay, so independent variable x, independent variable y, independent variable z actually. Fine. So here what is happening actually, when the u velocity is changing, when the v velocity is changing, when the w velocity is changing with respect to x, y, z, these things are noted actually. Okay. So this is one thing. So this is for full form. Let us take the 2D flow. For the 2D flow, what happens actually? So the u bar will be equal to capital U of I cap plus V of j cap, and this gradient will be dou by dou x of I cap plus dou by dou y of j cap. So when we do the dot product of these two, okay, what happens? Dou by dou x of u plus dou by dou y of v. So this is what we have for divergence. Fine. Next, for now let us see the physical meaning of the divergence. So what exactly is a divergence, and how do you basically generalize it, the divergence? And in terms of a fluid element moving with respect to one point to other point, so how do you justify that divergence? So these things. So let us take a fluid, let us take a control volume. So let us take this as CV. So you consider a fluid element actually. Okay. So the volume is dV actually. Fine. So if this is stationary, what happens actually? So the fluid will come inside and it will leave actually. Fine. So if you take this as control volume and it has some mass. So mass m is equal to, we have density into volume actually. Fine. So if let's say the control volume is fixed in space and it is not moving, then what happens actually? So the volume is constant. Okay. And so basically what happens, the density changes, and so therefore like to keep the m dot constant density may happen, or let's say the flow rate is affected by the change in density actually. Fine. Now the same control volume if you take, so let's take this is the, so this one is stationary, and basically this is called moving control volume. Fine. So take the same particle. Okay. So this is actually moving with velocity. So you take control volume V. So this is dV actually. So it is moving once particular velocity. So let's say the velocity of the control volume is, let us take this as BC. So when it is moving from this certain region A to other region, let's say this is B. So the shape of this control volume is just changing, let's say. Okay. So here there are two entities. So one, so you can say this as dV1 and this is dV2. Now the control volume, which is fixed in space, what happens actually? So the volume is constant, and therefore there is no variation of basically the control volume. Now here the same other aspect where the control volume is moving with the flow. So basically what happens? Control volume is moving with the flow. When it is moving with the flow, let's say from station 1 to, let's say, station 2, what is happening from station 1 to station 2? So the volume is not constant, the density is not constant actually. So basically here the mass is constant. Here the mass can vary. Why? Because the volume is stationary. So sometimes you have lower amount of flow rate, and sometimes you may have higher amount of flow rate, An example, you can take a tap. So when you open the valve fully, so the flow rate of water will be different. And if you open the valve of the tap half, the flow rate of valve will be different. If you open the valve of the tap 1/4 position, then the flow rate will be different. That is one aspect. And the next aspect, when you have the control volume which is moving with the flow, so the same number of the fluid particles. So if you take the fluid particles, let's say your P1, P2, P3, P4, so on the fluid particles which is moving, so within the control volume, so we observe that, so when it is moving with certain velocity, always there will be a same number of fluid particles which is present inside the control volume. So here, when it is moving, so the mass is taken as constant, but here, what is mass actually? Density into volume, so which is equal to constant. But here, the density, when it increases, the volume decreases. Fine. So what is happening? If the density increases, the volume decreases. Next, if the density decreases, the volume increases. Fine. So what happens actually, if you multiply both, it will make constant. So here, what is happening actually? So the rho, if it is decreasing, we will increase. If the rho, if it is increasing, we will decrease actually. So basically, if you have more number of particles, let us take a balloon actually. So if you inflate balloon with more amount of air, what happens? The volume of the balloon will keep on increasing actually. Okay. So same, if you decrease the flow of the balloon, what happens? The balloon will get, let's say, deflate, and the volume of the balloon decreases. Similarly, you can imagine the same scenario of the control volume, basically, which is going within the flow. So what happens actually, if you have more number of particles, your volume will increase. Where if the more number of particles are present, then we say that the density is high. And if you have the less number of particles, let's say the volume will decrease actually, but it will maintain the conservation of mass. Let's say the mass is constant. Okay, so the mass basically it is taken as constant. Fine. So this is what we have. Next, so when we actually change, let's say you take a fluid element approach. So here the volume is dV. So it is actually traveling to certain region. So the change in volume. Okay. So basically the divergence del dot V bar is nothing but, so the change in volume, okay, per unit length, okay, per volume. Fine. So basically, so along this length, fine, this is, let's say, this is length L. So the divergence, the physical significant divergence is change in volume per unit volume with respect to that particular distance. So is nothing but your physical significance of divergence. So the divergence will give the information of the flow, whether it is getting compressed and how the control volume will behave. So whether it is compressing, or let's say let's say it is actually expanding. So when it is expanding, what happens? So the volume changes, and this basically this one will, let's say, the volume changes, and here it decreases, and here the change in volume per unit length can be seen clearly. So in this way, the divergence is helping to visualize the flow with respect to change in length per unit volume. But if you see the mathematical point of view, so let us take actually a fluid element 2D. So here you have velocity, u velocity. Here also you have u velocity. Let's say here you have, let's say, v velocity. Here you have v velocity. When you apply divergence, so what is happening actually? So del dot, let's say, u bar is equal to, so dou u by dou x plus dou v by dou y. Now, what is the meaning here actually? So, dou u by dou x and dou u by dou y. So, when there is a change in velocity, so what is the amount of distortion that is happening? Let's say because of this inflow. So, if this is moving with respect to flow, this control volume, so the distortion happening along the y direction, distortion happening along x direction. So, because of this flow, let's say the new control volume shape, let's say it has decreased in this way. So, it has translated. So, the compression may happen or the elongation may happen. So when it is traveling from one region to other region. So basically the significance of divergence is to evaluate what is the change of control volume per change in control volume for the direction per unit volume. So this is the basic significance of the divergence of the control volume, and the divergence is actually seen in different aspects. So when you want to know in detail about a source and sink, so the divergence aspect is actually very helpful. So how much amount of let's say the flow is emitted through a particular source, and how much amount of radiation is absorbed through some sink. So these kind of things will be solved by divergence. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.